Okay, so today we're starting at looking at the photoelectric effect, where um, light is energy, and when light shines on things, energy can be transferred, and certain metals we can see a photoelectric effect, where electrons can be released from their different energy levels if the energy of the photon is enough. All right, so we're looking at um, probably the top few equations here today. These are just for energy states of a atom here, but what we're going to be talking about is the photon energy is E equals hf, right? But then F is can from the wave equation, F can be C over lambda, so E could be hc over lambda, or if we use it in electron volts, we could have that version of the equation. But our primary equation that we're talking about today is E is so this would be E either given to the atom or taken away from the atom. This one is mostly we're talking about light shining on a metal, and then it releases electrons. And so E would be the energy from the photon that's shining on the metal, and the metal has a work function. Just it's a property of the material, of the metal or what have you, that is the minimum amount of energy that it takes to release an electron. All right. So that's the work function, or some books call it the binding energy, right? So WO or BE are the same thing. And then, so the light will shine that much energy, or each photon will have that much energy. And then, so some of it will use to release the electron, and the extra will go to giving the electron energy to fly away at a certain speed, certain kinetic energy. Stopping potential V naught is we can get potential energy from charge times voltage. And so then if we we apply a voltage to the circuit, to the system here with this trying to release electrons, if we apply a certain voltage to it, and the energy is enough to stop the electrons, the energy will be enough to stop the electrons if we have the voltage is V naught times E, right? It matches the kinetic energy of the maximum. So let's look at this problem here, or these pieces of problems here. So a metal has a work function, binding energy of 6.8 electron volts. What is the largest wavelength that could eject an electron? All right. What is the largest wavelength that can eject an electron? All right, so remember, wavelength is C times F, and so wavelength and frequency multiplied together give us the speed of light, which is a constant. So if a wavelength is longer, the frequency is smaller, and vice versa, right? So we could also say the same thing, what is the lowest frequency that could eject it? But we're going with wavelength here. And so we're going to use our, so E for release is W naught plus KE max. Right, and so the smallest, so the longest wavelength, right? So we were looking for the least amount of energy to give it, right? That would correspond to the longest wavelength. And so the least amount of energy to give the metal would be when the KE max is equal to 0, right? So the electron gets out, right? This is the escaping energy, the binding energy, how much energy it takes it to escape, the work function. It gets out, but then it has no energy to go anywhere, right? And so when E equals omega naught, W naught is the maximum wavelength, minimum frequency to get an electron ejected. This is per photon kind of energy. And so that's going to be equal to H times F, but we want it in terms of lambda, so it's going to be HC over lambda. All right, so we're going to set W equal to HC over lambda, right, to find the lambda that we need. Remember, H is a constant, C is a constant. And so we can rearrange this to get lambda. So let's write the E, or not the E, the W naught over here. And so if we multiply by lambda, divide by W naught, we can get an equation here. So we've got lambda is HC over W naught. All right, and so we can plug in numbers here. We need H. H is Planck's constant here, 6.626 times the negative 34 joule seconds. 6.626 times 10 to the negative 34 joule seconds times C, which is speed of light, 3.0 times 10 to the 8th meters per second. And then omega naught, I'm sorry, what? W naught, I don't know why I want to keep calling it omega. The work function is, for this made up material, is 6.8 electron volts. But we got joules and electron volts, two different units here. So we need to get this into joules, I would say. So we have 1 joule, or 1 joule, 1 electron volt is 1.602 times 10 to the negative 19 joules. Is on our equation sheet also. All right, I think we got everything in there now. Let's get our calculator going. 6.626 E negative, that wasn't just negative 3, negative 34 E to negative 34 times 3E8 divided by, put in parentheses, 6.8 times 1.602 E negative 19. Okay. 182 times 10 to the negative 9 nanometers. All right, so that's part A. Part B, what is the lowest frequency? Okay, so since E is HF, I don't have that written anywhere. Anyway, E is HF, and so the lowest frequency means lower frequency means lower energy, right? And like we just said, was longer wavelength. And so this was the longest, lambda max. But now we want F min, right? And so it corresponds to the same minimum energy, same argument, basically no kinetic energy left over for it to go, but it did get out. So F min is just using this equation, F divided by C divided by lambda for the max, right? And so it's 3 times 10 to the 8th meters per second divided by the maximum wavelength, 182 times 10 to the negative 9 meters. So it ends up being 1 over seconds, which is hertz, right? And so 3E8 divided by 182 E negative 9. A very big number. So we get 1.65 10 to the 15th hertz. I don't remember what 10 to the 15 is. We'll just leave it as that. Okay. So maximum wavelength, minimum frequency, minimum energy to release something. Okay. C. Now assume that lambda equals 150 nanometers. What is the maximum velocity an electron could have? Okay, so we're going to have a new lambda. Lambda is 150. So just checking, it's less than the maximum, so it will have a higher frequency, so it will have enough energy to release some electrons. It's not a trick question. Okay, good. So what is the kinetic energy? So this isn't this kinetic energy, it says kinetic energy max. So that's the most kinetic energy an electron could have hit by one of these photons, right? So some of them, if they're, depending on what shell they're in, what position they're in, they may take less energy or more energy, right? And so this is just a calculation of the one that has the most energy, and so it'll have the fastest speed. Okay, and so we want, let's just rewrite our equation for a minute. So E equals HF, or HC over lambda, is equal to the work function plus kinetic energy max. And we are looking for the velocity. So we need to remember that KE equals 1/2 mv squared, right? And so we're going to find the kinetic energy first, and then we can do the 1/2 mv squared stuff. Okay, so this says that KE max then is equal to HC over lambda minus the work function. So KE max equals H 6.626 times 10 to the negative 34 times C 3 times 10 to the 8th meters per second divided by lambda, which is now 150 times 10 to the negative 9 meters. And then the work function is the 6.8 electron volts times 1 electron volt, or 1.602 10 to the negative 19 joules for 1 electron volt. So this is multiplied here. Electron volts cancel, we get joules there. This was joule seconds, and so we get joules. Good. So 6.626 E negative 34 times 3E8 divided by 150 E negative 9 minus 6.8 times 1.602 E negative 19. See if we got everything put in there right. Looks good. Looks tiny. KE max 236 times 10 to the negative 21 joules. What is the energy of one tiny little electron? So that should be tiny. Okay, so that's the max kinetic energy. So it's going to be equal to 1/2 mv max squared, right? One max energy corresponds to max velocity. Since m is the constant, we're talking about an electron here, so this is the mass of an electron. And so V max is divide through by these and take the square root. So it's the square root of 236 times 10 to the negative 21 divided by 1/2 the mass of an electron. Is that on our sheet? Yay, it is. 911 10 to the negative 31. Kilograms, standard unit, so we're good. And so V max is square root 236 E negative 21 divided by, in parentheses, 1/2 times 9.11 E negative 31. Okay. It's going fast. 720 times 10 to the 3rd meters per second. All right. Again, these are just made up numbers, so I don't know if that's a very reasonable number or not. The wavelength is not a wavelength of light, right? And so I think it's too small. Anyway, we're just practicing with equations mostly. So that is part, we did B, that's part C. Part D, given an electron with a speed of 1.8 times 10 to the 6 meters per second, what is this de Broglie wavelength? All right, so it looks like de Broglie, but I think you say de Broglie, something like that. So the de Broglie wavelength, maybe we need to go even further down on our sheet. Okay, so some of it is down here. So here's our de Broglie wavelength on our equation sheet. That probably should be up here. Anyway, it's a little bit different idea. So de Broglie said that if light can act like particles, then maybe it would have a, because it has energy, it might have momentum, and then if it has momentum, then it is acting like a particle, right? And so then de Broglie was like, well, if light can act like particles, then particles can act like waves. And so he, anyway, so the de Broglie wavelength is a wavelength thinking like light can have a mass, act like a particle kind of a thing. And, but then we are applying this to things that do have mass and calculating their wavelength. So it makes sense when things are going really fast and really small, like electrons. Might have a wavelength, might have a, act like a wave. But when things are really big, the wavelength is so small that we can't even measure it. All right, so the de Broglie wavelength, lambda, is equal to Planck's constant over momentum, or remember momentum is just mv, so Planck's constant over mv. So we have an electron, and so we want the wavelength is Planck's constant over momentum, or over mv. Okay, and what are we looking for? We are looking for lambda. Okay, so we just need to substitute in. We have v, and we know the mass of an electron, or we can look at our sheet. So we got Planck's constant 6.626 10 to the negative 34 joule seconds, divided by the mass of an electron, which we just had over here, 9.11 10 to the negative 31 kilograms, and the velocity we were given, 1.8 times 10 to the 6th meters per second. 6.626 e negative 34 divided by a couple things in parentheses, 911 e negative 31 times 1.8 e6. Okay. I think I got everything plugged in correctly. And so we have 404 times 10 to the negative 12. That is tiny. Negative 12 meters is lambda. Okay, so even for an electron, the wavelength is very, very small. Even compared to light, we had nanometers kind of wavelengths, and so it's even smaller by a factor of 1,000. Okay, let's look at, that's D. Let's look at E. What is the wavelength of a 0.25 kilogram ball going 50 meters per second? Okay, so this is getting way into the unobservable kind of range, but we can do that, and I should have made it so it was a little bit different, but just plugging and chugging again. So lambda equals h over mv, so the wavelength is Planck's constant over momentum, and same constant here. The mass was given 0.25 kilograms. Oh. And the velocity is also given 50 meters per second. All right, so we thought that was small for the electron. This is going to be even smaller, but 6.626 e negative 34 divided by, in parentheses, 0.25 times 50. Yep, and so we get 53 times 10 to the negative 36 meters is lambda. So super, super tiny, so no wonder we don't observe that big things, or things that we can even observe, act like waves when they're traveling. Okay, so that is good for day 36.